We start in 3 minutes, I guess.
Okay, so let's get started with the fourth talk of the session. For that, we have with us Iman Marvian from Duke, who is going to talk about symmetric quantum circuits. So please, the floor is yours.
Thank you for the introduction. My name is Iman Marvian. I'm based at Duke University. In this work, I'm going to present some results on an ongoing project in my group at Duke. We study local symmetric quantum circuits, various properties of this type of circuits. These are circuits that are formed from local unitaries that all respect certain symmetry. For example, they're all invariant under rotations around Z. And then the first step of this problem, this project, we study the question of universality. According to a well-known result in quantum computing, we know that any unitary transformation on n qubits or n Qudits can be implemented by a finite sequence of local unitaries, two local unitaries, unitaries that act only on a pair of qubits or Qudits. Although this result was discovered, in the context of quantum computing around 94 and 95, but you can argue that it's actually captured a more fundamental fact about dynamics of local quantum systems. It basically says that although locality puts various constraints on the short-term dynamics of the system, for example, it implies finite speed of propagation of information, it doesn't restrict possible time evolution that the system can have after a sufficiently long time. If you give the system enough time, it can experience any arbitrary unitary evolution. In other words, locality alone doesn't restrict the possible time evolutions that a system can have. Now, in this, the first step of this project, we ask if this universality holds in the presence of symmetries. Clearly, if all the local unitaries here in this circuit respect the symmetry, the global unitary that we implement also have that symmetry. Now, the question here is if we can implement a general unitary that respects the symmetry using local unitaries that respect the symmetry. Okay, so here is the outline of the rest of my talk. I will briefly talk about some motivations and applications for studying this problem. Then I will talk about a kind of surprising non-universality result. And specifically, I discussed the examples of U1, SU2, and SUD symmetries. And we will see a kind of surprising distinction between case of SUD with D equal to 2 and D larger than 2. This type is mainly based on these two papers. The second paper on SUD is enjoyed to work with two bright students at Duke University, Hanqing Lu and Austin Hulse. I think Austin is sitting somewhere in the audience. Okay, let's start. The framework of local symmetric quantum circuits has already become a standard tool in theoretical physics. People use it, for example, to study chaos, and in the presence of conserved charges, or they use it to classify symmetry-protected topological phases. And I would say it's kind of embarrassing that we still don't know some basic questions. We don't basic properties of this, this family of circuits. And there are some good motivations and applications to study this problem. In particular, first of all, by studying this problem, we can possibly find new conservation laws that hold when the system, the dynamics of the system respect both symmetry and locality. We know that symmetry implies certain conservation laws. For example, rotational symmetry implies conservation of angular momentum. But now the question is, if I have both symmetry and locality, are there any additional conservation laws that don't hold only if I have symmetry alone? So these new conservation laws will be a consequence of both symmetry and locality of Hamiltonian. The second motivation comes from quantum resource theories, such as, for example, quantum thermodynamics or thermality, resource theory of asymmetry, or related topics like quantum reference frame, covariant error correcting codes. In all these frameworks, in all these theories, the first assumption is basically that we can implement all family of unitaries that respect a certain symmetry. For example, in the context of quantum thermodynamics, defining assumption in this resource theory is that you can implement any energy conserving unitary regardless of the number of subsystems. So, for example, we assume that we can implement an arbitrary energy conserving unitary in the IID regime. Another question is that how we can implement these unitaries. If I'm restricted to, fundamentally I'm restricted by locality and I can't couple all systems simultaneously together, can I just realize a general energy conserving unitary by coupling, few systems together at each step and then via energy conserving unitaries? Or perhaps if I'm restricted by locality, then to implement a general energy conserving unitary, I have to implement local unitaries that are not energy conserving. And perhaps there's some hidden thermodynamic cost in implementing a general energy conserving unitary that we don't take into account, in usual resource theory of quantum thermodynamics. And the final motivation that I discussed in the paper, but I'm not going to, I don't have time to discuss it here, is synthesizing noise resilient quantum circuits. Generally, we can take advantage of symmetry to design more noise resilient quantum circuits. Okay, let's start by defining exactly what do I mean by symmetric quantum circuits. So this will be my running example throughout this talk. This is a U1 symmetry. I assume that I have n qubits in the system, and the U1 symmetry will be rotations around Z generated by Pauli Z operator. So Z here is Pauli Z. And so I'm interested in unitaries that commute with the action of the group here, or equivalently, unitaries that preserve angular momentum in Z direction, or sum of Pauli Z operators. Okay, so just to have some example in mind, in the case of n equal to 1, this will be all diagonal unitaries. In the case of n equal to 2, the Hilbert space decomposes to 3 sectors corresponding to Hamming weight 0, 1, and 2. And so in the Hamming weight 0, you can have arbitrary phase. In Hamming weight 1, you can have arbitrary 2 by 2 unitary V1. In Hamming weight 2, subspace with Hamming weight 2, you can have arbitrary phase again, right? And similarly for n equal to 3, then you will have 4 sectors, for example. And now I can ask the simplest version of the question that I want to study here. The simplest question is about 3 qubits. It's just about 8 by 8 matrices. Can I implement a general unitary in this form, in the form of this 8 by 8 unitaries in this form that are invariant under the action of the group, by applying two local unitaries that are in this form unitaries that are invariant under the action of U1, but they act only on a pair of qubits and they act trivially on the third qubit, basically, right? So this is the simplest version of the question that I want to study, basically. Okay, and of course, this is just an example of U1, but you can easily generalize this definition and this framework for arbitrary group exactly in the same way. Now, I defined the problem in terms of quantum circuits and gates, but equivalently, you can phrase this question in terms of Hamiltonians. You can think about the general Hamiltonian that can be decomposed as a sum of k local terms, and with the property that is commutes with sum of angular momentum in z direction, sum of Pauli's in z direction, and think about the unitaries that are generated by such Hamiltonians under Schrödinger equation. So this family of unitaries is basically equal to the set of unitaries that can be generated by k local U1 invariant unitaries. So by studying this problem, basically, we are also studying systems that are evolving under local Hamiltonians. Okay, so here is the first result. Kind of a strong no-go theorem. It turns out that in the case of continuous symmetry, generic symmetric unitaries cannot be implemented using local symmetric unitaries on the subsystem. Okay, so this is now I will show more, precise statements, but this is just a general idea. No. So the answer is no. It's not possible to implement, a generic symmetric unitary using local unitary operations. Now, you may say that maybe I can implement them approximately, even if I can't implement them exactly. But again, it turns out that the answer is no. The group generated by local symmetric unitaries is a compact connected Lie group, and and this means that if there is a unitary transformation that is not inside this group, then there's a neighborhood around that unitary that is not also here, and so we cannot implement it. Just to have a picture in mind, we can think of the group of all. So this is a schematic relation between the group of all symmetric unitaries and the subgroup generated by k local symmetric unitaries. You can think of the group of all symmetric unitaries as the torus, and the helix that is going around this torus is the subgroup generated by k local symmetric unitaries. And the point is the helix go back to its initial point, so it's just cover a small region of the torus. Okay, so in the case of U1 symmetry that I discussed before, it turns out that the difference between the dimension of the two manifolds is essentially n minus k. N is the number of qubits in the system. K is the number of qubits that can participate in a U1 local U1 invariant unitary. So this is the group generated by k local U1 invariant unitaries. Just to go back to the example that I discussed before, for 3 qubits, it turns out that the dimension of all U1 invariant unitaries is 20-dimensional, whereas the subgroup generated by 2 local U1 invariant unitaries is 19-dimensional. So 20 minus 19 is equal to 3 minus 2. That's what this equality says. Just to have, again, an example in mind, the family of unitaries generated by Hamiltonian Z tensor tree, ZZZ, that family cannot be implemented using 2 local U1 invariant unitaries unless, for particular values of theta, for example, theta equal to 0. And similar bound, we obtain a similar equality in the case of SU2 symmetry. In this case, the difference is given by the integer part of n half minus integer part of k half. Okay, now this is a general result. The previous result was equalities were about U1 and SU2. Now for general group G, I showed this bound. This is a lower bound on the difference between the dimension of all symmetric unitaries and the subgroup generated by k local symmetric unitaries. So the right-hand side, this EREPS Gn, this is the number of inequivalent irreducible representation of the symmetry that appears in the system, minus the number of inequivalent irreducible representation of symmetry that appears only on k subsystems, basically. Okay, so just again to connect this inequality to what we saw in the case of U1 symmetry. In the case of U1 symmetry on n systems, on n qubits, you have n plus 1 different Hamming weights from 0 to n, and this will be n plus 1 different irreducible representation of U1. And so this, in the right hand side, we see n plus 1 minus k plus 1, which will be n minus k, the identity that we saw before. Okay, so in general, for a continuous symmetry such as U1 or SUD, so this number of inequivalent irreducible representation grow unboundedly with n, And whereas, the second term, which is just the number of inequivalent Europe's on K subsystem is a constant. So in general, this gap between the dimension of this two manifold constantly grows with the system size. So the situation becomes worse and worse as the system grows, and this gap increases basically. Just to have a very rough intuition about what is the quantity in the right-hand side, at least in the case of abelian symmetries, I can interpret it as the maximum charge in the system minus the maximum charge that can participate in a K local interaction basically. That's just a very hand-wavy intuition about the quantity in the right-hand side. Okay, now this observation has an interesting immediate implication. It means that interactions that couple more subsystems together in the presence of symmetry, interactions that couple more subsystems together, they have a signature on the time evolution of the system, and in principle, by observing that signature, we can detect those type of interactions. In other words, we can probe the locality of interactions through experiments by just looking for this signature. So in the paper, I introduced a method for how we can detect the signature of these non-local interactions. Again, just to have a simple example in mind, suppose I have a general symmetric Hamiltonian HT, which can be decomposed in this form of H0T plus gamma T times some another symmetric term which is non-local. So you can imagine, this first term is just an unknown symmetric Hamiltonian with two local terms. The second term is an unknown non-local interaction. For example, a hypothetical correction to the Coulomb law, for example. And then the claim is we can observe the signature of this term on the time evolution of the system. And it's also important to know that to observe this, the signature, we don't need to prepare states that break the symmetry. For example, in the context of, for example, electric charge, we don't need to break the superselection rule corresponding to electric charge and prepare states that contain, superposition of different charges. We can just prepare, basically an entangled state, and using that entangled state, which is invariant under the action of symmetry, it has a, a definite charge. We can probe this, these non-local effects basically. Okay. Now this result, of course, I think is interesting, but it may be void because, again, in all these resource theories, thermodynamics, asymmetry, again, the first assumption is we can implement an arbitrary symmetric unitary, an arbitrary energy conserving unitary. But now the question is how we can implement them. Fortunately, it turns out that at least in some cases, we can circumvent this using an ancillary qubits. For example, in the case of U1 symmetry, I showed that a single ancillary qubit is sufficient to implement a general U1 invariant unitary. So a single ancillary qubit, which is either prepared initially in, say, 0 or 1. Okay. Note that, if you remember the identity that I showed before, the gap between the dimension of these two manifolds is n minus k. That means that even if k is equal to n minus 1, even if you can implement that unitaries that couple n minus 1 qubits, is still without ancilla, without a single ancilla. You cannot implement a general U1 invariant unitary. But a single ancilla then is enough to circumvent this strong Norgos theorem. Okay. And actually, you don't need, if you are allowed to use that single ancilla, then you can implement a general U1 invariant unitary just using interaction XX plus YY and a local Z. Okay, and then in the context of quantum, we can generalize this in the context of quantum thermodynamics. Just using a single ancilla, we can implement a general energy conserving unitary, right? So this single ancilla in the context of quantum thermodynamics, this ancilla will be either in, say, 0 or 1. This can be interpreted as a catalyst. But I want to mention that, in principle, you don't need a catalyst if you can also interact with a large thermal bath. There's another way to circumvent this Norgos theorem. So in principle, catalyst is not necessary if you are allowed to interact with a large thermal bath. Okay, next I want to focus on the case of Qudit system with SUD symmetry. So here is the setup. I assume that I have n qubits. So parameter d here determines the dimension of these local subsystems, but it also determines my symmetry. So my symmetry is SUD. So in particular, I'm interested in unitaries that are two local and SUD invariant, and any unitary in that form up to a global phase can be written as e to the I theta swap. So PAB here is a swap unitary that exchanges the state of qubits A and B. Okay? And so basically here we are studying the family of circuits that are formed from just e to the I theta swap for different values of theta and for different pairs of qubits. Equivalently, I can define this problem as a studying time evolution under Hamiltonian that can be written as a linear combination of swaps. Again, this is the same problem. And in this case, we found a kind of very surprising result. The fact that there's a big distinction between d equal to 2 and d larger than 2. For example, a Q3 and with SU3 symmetry. For d equal to 2, meaning that for qubits with SU2 symmetry, rotational symmetry, all the restrictions that are additional restrictions that are imposed by locality are restrictions on the relative phases between different ERPs of the symmetry. In this case, between subspaces with different angular momenta. Those are all the constraints, only on the relative phases. On the other hand, for SU3 with Q3s, now you also have, in addition to these restrictions, you also have restrictions inside these subspaces. Even if the state is restricted to a particular ERP of SU3, still you can have a restriction. So let me show you an example of that restriction. This is a simple system with 6 Q3s in this state. So 0, 1, 2 are just an orthonormal basis for a Q3. So this is 3 of those Q3s are in the single state, 3 of them are all in state 0. So this state is restricted to a subspace with only one single ERP of SU3, that is denoted by that Young diagram. And for this state, it's easy to see that with a general SU3 invariant unitary, you can map this state to any superposition in the form of alpha, singlet tensor 0 tensor 3 plus 0 tensor 3 tensor signet. Basically, this is a superposition of the original states and the state that is obtained by swapping, the first 3 Q3s with the second 3 Q3s. Right, there are many trees there. But it turns out that under 2 local SU3 invariant unitaries, you can generate a general superposition like this. You are restricted if you can only implement 2 local SU3 invariant unitaries. You can either generate the original state, obviously, or you can generate, this state that is obtained by again swapping the first 3 Q3 with the second 3 Q3s, but nothing in that form of the superposition. Okay. Interestingly, it turns out that we can actually circumvent this no-go theorem again with the catalyst. In this case, the catalyst will be 3 Q3s in the singlet state. And if you add that singlet to this, the initial state, then using just 2 local SU3 invariant unitaries, you can create now this superposition and you can return your catalyst totally unchanged in its initial state. Okay, so it turns out that there is actually a new type of conservation laws that capture this type of no-go theorem. There is a conservation law that holds under 2 local SU3 invariant unitaries, and it takes different value for this state and those superpositions. And because of this fact, we have we can understand this no-go theorem. Let me show you one example of those functions that are conserved. Here is an example: the function fs, g, and psi. This is a summation over all permutations. Sn is a group of permutations over n subsystems, basically. And P sigma is, the action of the permutation, basically. And SGN is just parity. So, any permutation has a parity, which is either +1 or -1, depending on the number of transpositions that you need to realize that permutation. And so this is the function. So it turns out that this function, as I will show you in a second, is conserved under 2 local SU3 invariant unitaries, or 2 local SUD invariant unitaries, but it can vary under general SUD invariant unitaries. So to have just a rough intuition about what is this quantity, this is a strange quantity. This quantity can be interpreted actually as a probability. So in particular, it's always between 0 and 1. And it's the probability that 2 copies of a state is in the totally antisymmetric subspace. So totally antisymmetric subspace with respect to the action of group Sn when it acts on a pair of qubits. So when it acts on the pair of qubits, then this will be the probability that 2 copies of psi is in this totally antisymmetric subspace. Okay. Now the fact that this quantity remains conserved, in fact, is related to is a consequence of a type of Z2 symmetry, a very strange kind of Z2 symmetry. The Z2 symmetry that is related to the notion of parity of permutations again. Just to quickly explain the idea, if you think about a general 2 local SUD invariant unitaries, which can be written in this form. Now, suppose I multiply 2 of these 2 different unitaries in this form, then you can break this, this unitary in this particular summation, where the first term only includes permutations that are even parity, And the second term has only permutations that are in only odd parity, right? And now there's another thing that's also going on in this summation. The first term has only real coefficients, and the second term has only purely imaginary coefficients, right? And in particular, this means that if you write this permutation, for example, in the computational basis, always all terms with even parity appears as real terms with real coefficients, whereas all the terms with odd parity appears with purely imaginary coefficients, right? And this, as you multiply, you can easily see that as you multiply more and more terms, this pattern always exists. Purely imaginary with odd parity and even real numbers with even parity. And this has a consequence. And that conservation law is basically the consequence of this kind of restriction, basically. So, proving that this is, this quantity remains conserved is not hard, but I didn't believe it until we really did the simulation. So we looked at the system with 6 Qubit rates under this initial states, and first we let the system evolve for, under 2 local Hamiltonians that can be written as a sum of 2 local terms with SU3 invariant terms. This quantity happens to be initially 0 for this state and remains 0 under those terms because, it's conserved. But then we turn on terms that are now SU3 invariant, but they are not 2 local. And then this quantity starts changing, right? And then, we then, at t equal to 300, we turn on terms that are not necessarily 2 local, but still respect that symmetry, that symmetry or parity that I explained before, and then again this quantity remains constant. Now it turns out that this is a very rich problem actually. There's a lot going on in different sectors, and basically, roughly speaking, you can understand these restrictions in terms of 3 types of constraint, roughly speaking. So you have constraints on the relative phases of different sectors with different errors of the symmetry. You have constraints related to the Z2 symmetry that I just showed you, and you have also constraints related to a new type of mapping from Qudit subspaces. Certain subspaces of the Qudit system can be mapped to a free fermionic system. Well, to be more precise, certain subspaces of the Qudit system will be mapped to a free fermionic system if the dynamics happens under 2 local SUD invariant unitaries, or under 2 local SUD invariant unitaries. But if you have, for example, 3 local SUD invariant unitaries, the corresponding fermionic system will be interactive. So, I can't go through the details. It's a very simple idea, but it's a very simple and powerful idea, but I won't be able to cover it here. So I just quickly skip. And let me just mention that there's an important previous related work by Iman Marvian from 2007 in the context of Lie algebras. He basically obtains the decomposition in simple factors of the Lie subalgebra of the group algebra of the symmetric group generated by transpositions. And some of the results that we obtained here can also be understood using his much more advanced techniques. But in fact, I think it's interesting. One of this fermionic correspondence that we find in our work actually, in my mind, explains a very mysterious and very remarkable result that Marvian has found based on just the fact that that result is about dynamics of free fermionic system. As soon as you have this observation, then you can understand a lot of those mysterious behavior that is not under, that look strange without this observation. Okay, sure. Let me finish by this slide. So this is just a summary, and I just want to finish by one sentence. So in this case, I study, in the context of resource series, I asked this question: how we can implement these local, how we can implement general free operations. I think this is a question that we should ask in any resource theory, or you should always worry about how we want to implement this set of free operations. In particular, can we implement them using local free operations or not? Let me stop here. Thank you.
Thank you very much for the very nice talk. We don't have time for questions, sorry. So if you have any questions, please contact the author afterwards.
Sorry for going over time.